Alright, ladies and gentlemen, now that we have a little bit of basic trig knowledge, our goal in this video is to fill in all the gaps that we need to get to the unit circle. So this is kind of scary looking, and notice we have a lot of stuff going on. We have all these degree measures, which we're familiar with, and then we have these measures with pi in them. These are radians measures, so for example, 60 degrees means the same as pi over 30 radians. So we'll talk about that in this video, and then we have these measures on the outside which are actually sines and cosines. So we'll start to develop where those numbers come from. While this looks scary, and you were probably asked to just memorize it, you don't understand it yet, it is really as simple as your multiplication chart here. So at some point in your life, you didn't really know what 7 times 8 was off the top of your head, but you knew how to look it up in this chart, right? So this chart was kind of a shortcut that you use until you memorize these facts. Unit circle is the same way. And like the most important thing, right, is eventually you learn to count by 8s to get to 56 or something like that. What I want you to learn is how to derive this unit circle. So if I ask you what sine of pi over 4 is, I'd want you to be able to figure that out, just like you could figure out 7 times 8. So we have a little ways to go. The first thing we need to know about here is special triangles, and hopefully this is a review from Algebra 2. So we're asked here to find sine of A. We're told that these are isosceles, and all that means is that this side is also 10, same as this side. And if this side is 4, this side is also 4. So that's what isosceles mean. So now to find sine of A, we would need the opposite side over the hypotenuse. And notice we don't know what the hypotenuse is yet, so I'm going to do first 10 squared plus 10 squared. And that side's called x, so I'm going to say x squared. Obviously, we get 100 plus 100 is 200. So I'm going fast here, but this is just Pythagorean theorem. And then square root of 200 would be x. And then I'm going to simplify that. So that's equal to 10 times the square root of 2. So that is my hypotenuse, is 10 root 2. And then sine of A would be opposite over a hypotenuse, which is 10 over 10 root 2. And look what happens here. And then we can rationalize, and we get root 2 over. Now, over here, if I follow the same pattern, we want sine of B. Well, I again have to do 4 squared plus 4 squared equals x squared to get my hypotenuse. But I'm going to start to think, like, what's the pattern here? And I'm going to use the pattern to be like, okay, x is also 4 square root 2. Okay, so if we got 10 square root 2 over here, that's the same as 4 square root 2 over here. It's the same pattern, right? So if I did my Pythagorean theorem out fully, I would end up with a 4 in front of square root 2 after I simplified. So then sine B is going to be equal to, this time, 4 over 4 square root 2. And then again, when I rationalize and simplify, I get root 2 over 2. Okay, so we're already starting to see how this pattern can help us solve these, right? So I already, just using patterns, had to do less work than I did before. This is a special triangle. It's a 45, 45, 90 triangle is our first one. And to draw my special triangle, my very simplest special triangle would be 1, 1, and then 1 square root 2 with a 45-degree angle. So that's my first of 2 special triangles that we're going to be using. My second special triangle really makes our lives easier here. So we're asked to find cosine of A and cosine of B. And I label A and B for you. So cosine would be adjacent over hypotenuse. So cosine of A would be, in this case, 10 times square root 3 over 20. And notice this kind of simplifies. My 10s cancel out, right? And I'm left with the square root 3 over 2. And the reason that knowing these relationships is so helpful to us is cosine of B, well, look at this, right? So it's going to be 7 square root 3 over 2 over 7. And this is a mess, right? And like, I'm probably going to mess up simplifying these fractions. Well, actually, the relationship is the same anytime, right? So no matter the size of the triangle, if it's a 30-degree angle, that will always reduce to root 3 over 2, just like we saw on the previous one. This special triangle is a 30, 60, 90 triangle. And 30 is the smallest angle, right? And the simplest version of this is 1, 2, square root 3. So that's our second of two triangles, and again, it's a 30, 60, 90. Okay? And the reason that knowing these now is so important is that it gives us a reference for these really common angles. So 30 degrees, 45 degrees, and 60 degree angles are the angles that most often show up in real life. And if I can draw one of these triangles, I can figure out these ratios in exact terms without a calculator. So for example, we already figured out that 45 degrees is root 2 over 2 for sine. And that, let's see, 30 degrees, the cosine is root 3 over 2. And what I'm going to ask you to do is pause the video now and try to fill out this table on your own using our two reference triangles here. And I'll give you the solutions in a few seconds. Okay, so notice we have a couple patterns here, numbers that repeat. So 45 has the same sine and cosine, and that makes sense because they're the same side lengths in that particular triangle. And then what we see is sine and cosine are flipped right here. And then same goes for cosine of 30, sine of 60. And that makes sense because those two angles are complementary, right? So sine A should equal cosine of B. Okay, so there's our reference. We're going to use these to figure out sines and cosines on our unit circle eventually. One more thing to add about special triangles is that we can also use them to solve for sides. The way I like to do this is I like to label using A, just like I gave you in your notes. This would then be 2A, and this would be A square root 3. So notice A, the shortest side, goes across from the smallest angle. And this is a 30, 60, 90 triangle, so if it was a 45, 45, 90, I'd label it differently, obviously. And then I can just make an equation. I can be like 2 equals A square root 3. A would be then, if I divide by square root 3 on both sides, 2 over the square root of 3. And then if I want to find x, that's 2a. So 2a would be 2 times 2 square root 3, which is just this, and then we rationalize. Okay, so the way I would suggest you do these is by making equations to solve them. All right, home stretch here. The last thing we need is that units piece. So mostly we're going to be working in radians, although you're more familiar with degrees. So what you need to know to do this, and you've done this before, it's the same as converting feet in inches, is the conversion factor, right? So a whole circle, as you know, I think Tony Hawk, is 360 degrees. That is equivalent to, in radians, 2 pi radians. Okay, so to do a unit conversion, say we want to turn our 30 degrees into radians, we'd say 30 over 360 is equivalent to x over 2 pi. So that's what we're trying to figure out. And then I'm going to cross multiply. I'm going to be like 360 x equals 2 times 30 is 60 pi. And then I have to divide by 360, and I get x equals 60 over 360 times pi. And then this reduces to simply pi over 6. All right, so that's the conversion process. And notice what we're going to do here now is fill out a table. So pi over 6 is 30 degrees. By the same process, this is 45 degrees. And I would be like, okay, x over 360 equals pi over 4 over 2 pi is one way you could do that. And then here's 60 degrees. Well, it's 2 times pi over 6, right? So it would be pi over 3. So those are our special angles in radians. And the last thing I'm going to have you do for me, and you'll do this on your own, is I'm going to be like, here's my table again from the first page, but I'm going to use, put in the same order, I'm going to use my angle measures now in radians, so I have that reference as well. And this should match then this table that we made together earlier.